Hello, ladies and gentlemen. Welcome to 2018 Elite Engineers webinar. My name is Raphael, software consultant from MIDAS, and currently in charge of the webinar. So today's theme is modeling, analysis, and design of steel double composite top girder bridges for SPMT. The purpose of this webinar is to deliver the insights to engineers so that we can improve the overall performance of the bridge industry. Also, what we need to focus here is how MIDAS Civil can benefit and how Marco managed this project in terms of modeling, element analysis, and construction sequences for the steel and complex bridge project. So for the engineers who actually want to try this, I prepared the trial materials that you can actually try using 30 days free trial. So please contact me after the webinar. I will mention about this later. So now let me introduce our speaker first. Then I will explain to you how to ask questions during the presentation. So Marco was currently structures, rail, and construction management group leader at Jacobs in Chicago. He manages all the structures for Jacobs in Chicago. He did both bachelor's and master's degree at the University of Iowa. He did civil engineering for the bachelor's and structure and materials for the master's. For the more detailed information about Marco, I will leave it to him. And let me explain how audiences can ask the questions. So to ask question, like you can see here on the left side, there is a question tab on the control panel. So first, please open the question tab and please write your question down here in this empty space. And third, please send the question. The other way to send me a question is you can simply use the chat function. When you see the picture on the right side, you will see this when you open the chat function tab. So please select send question to Steph. Then your question will be shared with Marco and me, or you can simply chat your question. So I will gather all the question and share with Marco so that Marco can answer the questions after the presentation. So now I'll pass the authority to Marco. Hope you guys enjoy. And if you have any problem, please use chatting function. So I will stand by here. So please welcome Marco.
Hello, everyone. My name is Marco Loredo. First of all, I would like to thank you for the opportunity to present. Thank you, Raphael. Just a brief introduction about myself. I think Raphael did an excellent introduction. Just to complement, I'm here based in Chicago for Jacobs, and I primarily work on large design build projects, and our group here currently works on the California High-Speed Rail and Westgate Tunnel in Australia, Melbourne currently. And the project that I'll be presenting today, this was in Adelaide, Australia. And primarily my experience has been with design build projects. So I'll start my presentation with a brief, hold on, I'm having some technical problem here. Okay. Okay, so I'll start with a brief agenda. I'll be talking about the project location, overall background, and the design concept. And most importantly, we'll talk about the structural analysis and how we achieve or how we perform the structural analysis, as well as the structural design of the composite girders, and how we went about to model the SPMT move. So let me give a brief introduction on the project location. This project was in Adelaide. Adelaide is located in central South Australia. It's the 5th most populated city in Australia. So as part of this project is the north-south corridor. So what you see here on the screen, this north-south corridor extends all the way from north to south through Adelaide main district, the central business district, and it's about 78 kilometers long. So several years ago, the government of South Australia decided to improve the entire corridor, mainly because there are several bottlenecks across this corridor. So to date, out of the 78 kilometers, there's about 44 kilometers of the north-south corridor that have been completed, and it's pretty much to alleviate the at-grade crossings between local roads and main expressways. So what you see here on the screen on this little orange segment, and that's the Darlington Upgrade Project, that's where we're currently working. This section is only 3.3 kilometers. Total construction cost for this segment is about $620 million. Jacobs is on the design venture. As part of this project, we are the engineer of record. Here what you see, these are the project limits and the main limits of the overall project, but I just want to point out to some of the main roads and expressways. In green here, what you have is the Southern Expressway that meets with the South Main Road in blue. So this green and blue intersection, it has major traffic congestion, carries a traffic vehicle, more than 75,000 vehicles per day. So this is a major bottleneck because it's an at-grade crossing. I will show you a closer detail to that. But here at this particular location, that's where the two of the SPMT move occurred. That's primarily to install the bridge without interruption to traffic at this busy intersection. The other point I would like to point out to you is Sturt Road, which is it is here in red, crossing Main South Road. This also is a major bottleneck on this project. There's about greater than 90,000 vehicles per day on this intersection, creating major bottlenecks as well. And there's three important things that we need to note here is in this yellow square, that is Flinders University, major university in Adelaide, and in red square here, we have Flinders Hospital, which is the largest hospital in Adelaide. And up in blue, you have a commercial and industrial complex along this corridor. So there, throughout the corridor, there's major bottlenecks. And the main objective of this project is actually to take Main South Road and depress it and make it a non-stop corridor. I found this interesting because I was checking on Google Earth, and lo and behold, this was actually taken last year when they were building the bridge off-site. But here you see up on the upper right corner of the screen, you have Southern Expressway and the Main South Road that cross, and that's where the major bottleneck occurs. So on the south, which is what you see here is the bridge. This is bridge number 2. This was the first bridge moved into place into this intersection here for the Southern Expressway and Main South Road. And right next to bridge number 2, you can actually see the steel segments being erected for bridge number 3. So between the spot where the bridge was actually built to the intersection, it's approximately 1 mile. Closer screenshot to Southern Expressway and Main South Road. So that's where actually 2 of the bridges were installed. The first bridge was installed last year around November 24 and 25th during U.S. Thanksgiving. And then the second one was actually installed last weekend. So bridge number 2, the one I'm be talking about here today, was installed first. And then just last weekend, bridge number 3 was installed. But what I want to point out here is that Southern Expressway, as you can see, it's an at-grade crossing. You have 7 lanes at Southern Expressway, and you have about 8 lanes at this point with the Main South Road. So this creates a major bottleneck condition. I did mention about Flinders University and the Flinders Hospital. So you see here Flinders Drive is just a little access road, and then creating this at-grade intersection with same main road, which again creates a bottleneck and creates difficulties for emergency vehicles accessing the hospital as well as students going to the university. Going further north, we have Sturt Road and Main South Road. This is another major bottleneck, and here the situation actually gets worse because Sturt Road is 9 lanes, and then Main South Road turns into 11 lanes. So like I said before, the overall objective of the project is to get Main South Road and actually depress it, so we eliminate the at-grade crossings, and all the structures now are elevated over Main South Road. Now, as part of the project, as far as bridges, there's a total of 8 bridges being constructed across this corridor to improve the connectivity and the traffic flow in the area. I would like to point out to this is where we erected these 2 bridges that I just mentioned, but there's another one, which is the Ellipse bridge that is going to be erected further north, which is here on the right corner of the screen. So this one is going into place in the next 2 weeks. So in total, there's going to be 3 SPMT moves as part of this project. So here you can see is the final design concept, which now is a reality, is not a concept anymore. Where my cursor is pointing here, that this is actually bridge number 2. So bridge number 2 had to be installed first, and then last weekend we installed bridge number 3, which is adjacent to it. Obviously, the reason that we had to do bridge number 2 first is bridge number 2 would come first, and then bridge number 3 would come second. So bridge number 2 will take Main South Road and actually divert that to local traffic, and then bridge number 3 will actually take vehicles down the main expressway, so eliminating all at-grade conflicts. This is the overall layout of the bridge. This is bridge number 2, the first one. This was erected, like I said, last year. The overall bridge layout was about 600 feet long, total span. At the abutments, the girder depth was about 6.9 feet, and then with haunch girders that haunch up to 12.5 feet at the piers. There was a minor curvature to the bridge, which was about 2,500 feet radius, and the deck width was about 33 feet wide. That had to accommodate 2 conditions, one for the temporary condition with 2 traffic lanes, and then the final condition with 1 lane of traffic and then a pedestrian path. So what you see here is the cross-section of the bridge. One thing that I would like to point out is this is the temporary condition, which we carry 2 lanes under this condition. So the girders were with we use vertical web girders and precast panels. I'll show you more about the precast panels. So we have the precast panels and with a mix of casting place concrete deck. Here's the final condition, and this is actually a cross section that was taken actually at the pier over the negative moment zone. And what you see at the bottom here, this is the double composite action that it's created by actually putting concrete slab at the bottom, on the bottom flange at the piers. We apply some shear studs into that zone, so you create that composite action along the negative moment zone. Now, as far as the deck panels, the contractor decided to use a precast deck panel, and what you see here is actually the panel that was used. The panel in itself, and in Australia they call this transfloor slabs. The panel in itself is only 5 inches thick, and accommodates pockets for the shear studs. And then after the precast panels are placed, there is an additional 5 inches of additional casting place concrete that is placed. So total overall thickness of the deck is about 10 inches. And then the shear pockets, overall they were spaced every 12 inches. So what you see here is the transfer panel. This is not the actual bridge, but this is just the concept that is used in Australia. Transfer panel, they're primarily truss panels where you have these bars coming out of the slab, and then you have the transverse bars that are actually welded, so creating this truss action. And then here on the right, you have a different example of the transfer panels being used. But the difference here is that you actually have the barriers being monolithically with the precast deck panel, primarily just to expedite construction. We use a similar situation here for this bridge, but I'll explain later. But we were not able to use the the full barrier, primarily because our overhang was fairly long and create some undesirable bending stresses on the slab. So now let's talk about the structural analysis. As part of this project, we use MIDAS Civil for the bridge analysis. So there were some required models that we had to create. We create models, obviously, to analyze the live load condition. The temporary live load with 2 lanes control the design, but we also analyze for the final live load condition with the pedestrian path. And within the same model, we perform the analysis for the SPMT move. And in addition to our global models, we develop some local analysis models to perform some finite element. And this was all done with MIDAS Civil and a combination of also MIDAS FEA. What you see here is the full 3D model that it was created. Deck where we use plate elements, as well as for the tubs and all the internal stiffeners, transverse stiffeners included. We use plate elements, and then all the internal cross bracing, what we use was just beam elements. Now, the goal of the 3D model was not necessarily to do the full design of the bridge, even though we did a verification. But the goal of the 3D model was primarily to analyze the interaction of the supports caused by the SPMT. And this is what you see here on the screen, where we have the stress plots. But if you notice on the right here, where we have these arrows pointing up, that's actually the placement of the SPMT supports. So we were able to determine what would be the local effects of the SPMT supports on the girder itself. So I would like to, before I go to the next slide, I would actually like to show you the MIDAS model, and this is just one of them. We have different ones because for different purposes. What you see here, the deck of this model, those are plate elements, and this is the global model. We use plate elements for the deck, and then for the girders itself, we use beam elements. What you see here, I'm just going to show you quickly, but this is we had to use the erection sequence because the bridge was constructed on temporary supports, and then with the precast deck panels, and then the concrete was poured, thus creating the composite condition, and then the SPMT came into play and then picked up the bridge and took it to its final position. But what you can see here, we did use the erection module within MIDAS, which is actually fairly simple to use. And in the same model, we performed the erection analysis at the same time we perform a creep and shrinkage for the concrete elements that is given here by this time-dependent material functions, as well as applying all the static load cases within the same model. The good thing, or I think it's a great thing, the great thing about using MIDAS is that the loading functions, because it does provide all the vehicles, and so working in the US and having to define all the Australian vehicles will be a very tedious process. But within MIDAS, you actually can get Australian loads, and just a click of a button, you can get your M1600 and your S1600. So here, what you have is all the loads that are already defined within MIDAS. And then since we do a lot of projects overseas, there are some other countries and live load vehicles that are very helpful, so we don't have to define them. So this is in a nutshell the global model. Now this is the overall beam design layout. So what you see here is just one section, and this section is over one of the piers. The gray section that you see here is actually the double composite, where we place the concrete on the bottom slab. And the reason for that, obviously, is that with bottom slab at the bottom, we're going to be more effective in taking that compression. One of the main challenges that we had as part of this project was the thickness of the web. So one of the goals of the contractor was to minimize the use of steel on the entire project. So we had to use a web thickness of 16 millimeters, and that's about 5/8 of an inch for the entire tub girder, which is very challenging when you start trying to design that for the deeper sections, because your D over T, D being the depth of the slab, depth of the box by the thickness of the web, the ratio goes up as much as 240. So as a result, we had to use longitudinal stiffeners, and this is what you see here on this elevation view with the longitudinal stiffeners. So the way that this bridge was being erected, so they would bring one segment, put over temporary supports, and this is what you see here. And after the bridge was so they would go ahead and put the additional segments, and after the bridge was complete, the SPMT would come in between the temporary supports, so they had to squeeze in between the temporary supports and then pick up the bridge and take to its final location. I will show you an overall, there's a video. I will show you how the bridge was fully erected, but this gives you an idea. So every time that a segment of steel was brought up to the field and placed in temporary supports, that was all captured within our MIDAS model. And then as the deck was cast as well, so we could capture the locked-in stresses on the structure. So what you see here is the concept of double composite. Again, it's primarily using the negative bending regions. What they say in Australia a lot is in the hogging zones. Not very common here in the US. We just call it negative bending, but it's something that I picked up fairly quick when I was in Australia. So this goes over the hogging zones, and primarily is because your compression is at the bottom slab. This concept is not common in the US. It has been mostly used in Europe, and currently is being adopted in Australia by a lot of the contractors. And as a matter of fact, on this project, we have several bridges that are using the double composite concept. Now, even though that this concept is not fairly common in the US, there's a very good research paper, a study done by the University of South Florida, and it was done in about 2010. We did get a hold of this study report. I think if you go to the website and Google it, you might be able to download it for free. But we use this study as a basis for our design. And one of the issues, and if you go over the study, there's a couple of issues that you have to address when designing for double composite. The first one is that, you know, there's always that urge to make your steel bottom flange as thin as possible. But there's a penalty that you pay for that, because if you make your steel bottom flange fairly thin, then what's going to happen is that what they found, that there would be debonding between your steel plate and your concrete slab at the bottom, thus creating local buckling. So we had to address this issue in our design by being careful and not to make the web too thin, and to be a little bit conservative as far as our design went. And the other issue that you have to address is that when you're pouring the slab on the bottom flange plate, if you have a wide box and you have a wide bottom flange with a fairly thin plate, because you're not under the composite state, the tendency is that the bottom flange is going to bulge out, and when the concrete hardens, you might end up with a bulged and hardened bottom flange. So this is another thing that we use our 3D finite element model to assess the weight of the concrete and how much bulging we're going to get. In order to compensate for the bulging, we increased the thickness just a little bit, but also we provided transverse stiffeners along the bottom flange. And keep in mind that the girder is haunched, so by having the transverse stiffeners, it helps pouring the concrete, so your concrete is not going to sag all the way to the bottom of the haunched girder. So as I mentioned before, we use shear studs, and the slab that we end up with when our design was done was about 250 millimeter slab, which is about a 10-inch slab on the bottom flange. So what you see here is the SPMT that was used. The bridge move was done by Sarens. So we had several SPMT located along the bridge for the pickup. As you can see, on each pier we had two supports, one on each side of the pier, and then one on each abutment. And obviously they had to squeeze in these SPMTs in between the temporary supports. So there was the first challenge. And this is how we had to approach the whole move. On the left, what you see here is the first turn. So they brought the bridge parallel to its final configuration, and then they had to swing the bridge starting on the south end first. And this was done because they had to clear the substructure of bridge number 3, which was the bridge that is going to be, it was placed last weekend. So they would swing the bridge number 2 south end first, and then they would maneuver the north end by rotating into position and then squeezing in. This bridge move took about, we had a time window of 54 hours, starting on a Friday night, and then we had to have it open by Monday morning around 3 or 4 in the morning. I don't recall it, but the reason being is that it could not impact a Southern Expressway and that intersection with the South Main Road, primarily because there were 75,000 vehicles. So we were under a tight deadline, but everything went well. The bridge move actually was done in less than 23 hours. The easy part was actually taking the bridge down the road, and the most complicated was actually to swing the bridge into position. So here I have a video of the bridge construction. This is on YouTube if you want to take a look. I know that you don't have the sound, and I'm going to mute. Okay, so what we're seeing here is the location of the bridge on the Darlington, as I mentioned, is the main South Road Bridge. This was the first one that was installed last year. So this is the erection yard. So they would first install the temporary support piers, and each piece of steel was then placed and spliced. And then we had the precast transport panels, and then we did pour the slab. They're showing that the bike path was poured, but it was not. This is incorrect. So we actually pour just the slab. Then the SPMT supports would come in, pick up the bridge, and then swing out to Main South Road. And from this point on, it was fairly simple. Now what you see here in green, that's a 3-meter exclusion lane, and that was to maintain access to the hospital, Flinders Hospital, for ambulances. Now, what is interesting here is that the bridge is actually crossing another bridge, which you see here by the river. And this small bridge had to actually we had to reinforce the bridge due to the heavy weight of bridge number 2. So, and here was the most challenging part, which is to bring the bridge in place. And you can see actually the substructure to the left there is the final substructure for bridge number 2, but we had to clear, by swinging the south end, clear the piers of bridge number 3, and then finally putting the bridge into place. So that was the schematics, and then we just install the wearing surface, and this is the final concept that you see over here. But this shows the completed bridge number 2 and bridge number 3. So going back to notes, going back to the presentation. Sorry. Okay. I don't want to show this again. Sorry. Some technical problems here. Okay. There we go. All right. So the way that we approach SPMT analysis. So again, this was all done in with MIDAS Civil. So when you're doing an SPMT move, there's different scenarios that you have to investigate. So let me start with the vertical settlement at any SPMT support. So imagine that you're at the SPMT support location, and that support actually settles during the bridge move, or when you're trying to put the bridge in place. So by having that support displacement, you have to account that for in your model, so you can see what the displacements are going to be on the overall structure, as well as the stresses that are generated not only on the steel elements but also on your deck. When you're dealing with a steel composite structure like this one, you'll see that when you're doing SPMT moves, the main concern is actually with the deck, because by being a fairly actually flexible structure, there's a potential for the deck to crack. As a matter of fact, what they do, they will do a deck inspection. So the joint venture, along with the client and their reps, would do a deck inspection prior to the move to map any cracks along the structure, and then they would have to do another deck inspection after the move to ensure that there was no excessive cracking. So we also had to look for transverse differential displacements between supports. So let's say you were looking at at just one support location, and then you have one support on the right that settles more than the support on the left, thus creating this differential transverse displacement at the support location. So you have to analyze for that case as well. And then the third case, and if you're familiar with SPMT moves, you see that is the twist case, and that's actually the one that tends to control the majority of the time. Is this actually the settlement between across two supports? So let's say you have one support at the abutment and one support at the pier, and then you have your support at the abutment actually going up and down, and then ending up twisting the deck. In the majority of the time, that's what it's going to govern, especially on the deck. So here's the analysis that we did using MIDAS Civil. So again, all the deck that you see here, those are plate elements. And when we ran the analysis, we had to come with several different settlement cases. On a simple span, that's fairly simple. You're not going to end up with a lot of cases to analyze. But in this situation that we have here, where we had actually 8 points of support, actually 6, right? 6 points of support and 1 on each side. We had several cases of settlement and twist. We had approximately 150 cases that we had to analyze. So what you see here is actually settlement taking place at one of the abutments, up and down. And then another example here where you have your pier SPMT at the piers settling down. So, and then other cases would be where the adjacent pier would settle, and then we would get all the deck stresses, and then you would have the opposite abutment settle. And here, this is what I was talking about, the twist, and you can see how stresses rise fairly quick when you have a twist case. So you see what you have here is abutment, what we call abutment B for this project. One side of the abutment going up and the other coming down, thus creating a twist on the deck. Now, by using this type of analysis, we were able to pinpoint what would be the key points where stress would rise fairly quick and where we had to control the displacements. So by doing this analysis, we were able to determine what would be the allowable limits, because that's one of the things that we had to give to the contractor. Contractor wanted to know how much my SPMT support can go up and down and how much I'm allowed to twist, and where I had to put my monitoring devices. So by doing this analysis, we're able to, like I said, pinpoint all the high stress zones, and then we developed a monitoring plan, and the monitoring plan included the use of strain gauges. So we placed strain gauges on the steel bottom flange as well as top flange. We also apply strain gauges on the rebar actually over the piers, because primarily that's where tension is going to develop, and we want to make sure that we minimize cracking, and as well as laser targets. And the laser targets were used to monitor the twist on the deck, and I can show you some of the targets. So what you see here are just some construction photos. This is the steel girder being erected on the temporary supports. And on the right side, what you see here at the bottom flange, this is actually one of the strain gauges. And then we apply another strain gauge at the top flange. Now, you don't need strain gauges everywhere. In this case, we apply strain gauges on the mid-span of the bridge because they're close to the high moment zone areas, as well as at the piers. Again, this shows one segment being connected to the other over the temporary supports. You see the splices here. This is the bridge when it's was fully built. As you can see, the SPMTs, they came in between the supports to pick up the structure. These are the transfer panels that were used as part of this design. I did mention to you early in the presentation that we didn't include the barrier to its full extent. So what we did, we only cast the outer shell being integral, and then the rest of the barrier, it was cast later on, primarily because we had a very large overhang, and by including the full barrier, we would not, there would be some substantial cracking and uneven distribution of the weight of the deck over the flanges of the tub girder. And this is just an infomercial that was put together by the authority. But the one that I like the most is that this bridge move was heavier than 75 humpback whales. I thought it was an interesting stat. And then here, this is the move for bridge number 2. And I'll try to show you a few details. So this was last year, November 24th, 25th. And one thing that I liked too was the barrier being colorful. It was very neat. So here they're getting prepped for the move, and we started this on a Friday night, and with the objective of being done by Monday morning. You can actually see the laser targets at the top. So these are all the laser targets that are going to measure the twist. So now we're backing out of the construction yard. All the traffic has been diverted. As you can see, there are lights because this movie is being done at night. So this is the operator. It's amazing, you know, the knowledge of the operator to move an entire bridge. While this bridge move was occurring, we were actually viewing it from the US via, they use Aquamonics. Aquamonics monitor all the strain gauges and the laser targets, and you can see the bridge being adjusted up and down here, primarily because the supports are settling and then they have to adjust, and now we're trying to swing the bridge into place. And pay attention on the last scenes, but here are the laser targets. So these are all measuring the twist. So you have actually a laser target on the opposite pier, and they're crossing diagonally each other so they can measure all the twists on the bridge. We found the laser targets actually to be more accurate than the strain gauges. The strain gauges are accurate, of course, but the challenge is that with strain gauges, you have a lot of noise that it gets generated, so your readings are not as smooth. With the laser target, as actually you can see the bridge moves taking place fairly smooth. So that was, sorry. So this was one of the advantages. And with that, I will end my presentation and see if you have any questions.
Yeah, Marco, thank you for the presentation. I gathered all the questions. If you have any other question, please send me, then I will show you. I will take the authority for the view. Yes, Marco, you can keep going.
So how is the deck plate element connected to the beam elements? Sharing the node or rigid link. If I recall correctly, we did use rigid links to connect the deck to the beam. Under negative moment, the deck will be cracked. How do you consider the stiffness reduction? So in the US, as well as the Australian code, you have, in the US, you can analyze the bridge as being, without being cracked throughout the entire structure. That's the approach that we use. And then we also use the Australian code. The Australian code has two ways that you can go. You can perform the analysis being fully uncracked, but then if you do that, you have to do a adjustment with a couple of equations. But the other option that you have is to crack the deck over the piers about 15% on each side of the center line of the pier, and that's established in the Australian code. We did analyze for both, actually, using the 15% and also doing for the fully uncracked. Have you considered 4 steel girder typical section versus 2 steel tub typical section, and why you selected 2 steel tubs for final? We didn't have much of a choice on that. Keep in mind that this is a design build that is also dictated by urban planning and architects. So we had to go with the steel tubs, only 2, and also with the vertical webs. As you know, you could do incline webs. This was not an option as part of this project. And so we had to go with the vertical webs. And as a matter of fact, going with vertical webs in a curved profile is actually easier to fabricate. So the goal, the overall goal of the contractor is, it's interesting because in the US we're primarily used to see savings on the fabrication and spend a little bit more steel. In Australia, it's quite the opposite. In Australia, the goal is actually to save on the steel, and they don't really care much on the fabrication, which I found interesting. And I thought it was just this project, but I'm currently working on the Westgate Tunnel project in Melbourne, and again, the contractor is a different contractor, but again, we're even having steel optimization workshops where we're trying to minimize the weight of steel at the expense of fabrication, so they don't really care about the cost of fabrication. How did you model MIDAS civil, the composite section at the bottom and top flange? Can you explain some details? Okay, so so we did use plate elements at the top. So we turn on the deck at the point that it had to obviously to become composite with the steel. And then within MIDAS, you can take your section resultant cuts. So you're basically combining your steel action with the plate elements. So it was not, you know, if you just do a beam element or with the simple standard sections that are given within MIDAS with the steel plus the slab at the top, it's fairly simple because you can just plot your beam moment diagram. But when you mix beam elements with the plate elements, then you actually have to take resultant cuts and create some virtual sections. So that's how we did it. As far as the composite section on the bottom, the cross-sectional properties, we just transform the concrete to an equivalent steel section. Okay, is there a companion paper on the steel box girder double composite design? The topic is interesting beyond the MIDAS application. So I didn't mention at the beginning of the presentation, we did write a paper on this, but we didn't get, you know, in detail on the overall design. If you are interested, I would highly recommend that you take a look at the University of South Florida study. I think they did a much better job than I could explain to you. As a matter of fact, they do present some of the calculations and how the approach is done for a double composite girder. So please try to get a hold of that study. It's very insightful, as a matter of fact. Okay, what are the settlement differential settlement values? Which code? Well, there's not really a code for this. And that's a very good question, right? Because how do we go about determining what is an acceptable settlement limit? Okay, so if you make your settlement too small, then what's going to happen is that the contractor is going to have to stop frequently and have to adjust the SPMT supports, and that's going to delay. Now, if you make your settlement too large, then you run the risk of cracking your deck and damaging your steel elements. So where is the limit, right? We did find, at first, we tried to limit just to the modules of rupture of the concrete. Well, the limits that we got were fairly small with that. You're getting in the order of 5 to 15 millimeters. And that was not an option because we would have to do frequent adjustments. So what we did is the following. At the moment that the bridge was picked up by the SPMT support, we recorded all the state of stress on the bridge. And from that point on, we said, okay, what are our peak points of stress? And we are going to allow a 100% stress increase on any of these high points of stress, and that's going to be our displacement limit. We did that, but obviously we did also check the stresses on the rebar over the piers, as well as the strength of the box, and the strength of the steel was never an issue. It was always the deck. But we did check again all the stresses, theoretical stresses on the rebar to ensure that even with that 100% increase, there would be no adverse effects. To give an order of magnitude, We had about 100 of vertical displacement at the abutments, and then approximately 20 to 25 millimeters of twist. Now, if you're planning to do any SPMT move, I gotta warn you. So what happens is, because we need to give strain values, so we had to get the stresses from MIDAS and then transform into strain, and then we had to give strain values for the strain gauges during the monitoring process. What we found out is there is a large fluctuation just in temperature gradient alone, and that has to be taken into account. Initially, we did not take that into account, but what they do is they will install the monitoring system several days prior to the bridge move, and we'll start monitoring just the overall behavior of the bridge. And you can see the variation in strain just by going from day to night, and then you have to take that into account on your move. The other thing that you also have to take into account is you give the limits to the contractor. We did give the limits to Sarens, and they did a calibration, which means they actually settled the supports on purpose to do that calibration. So they did push the bridge up and down the abutments 100 plus millimeters or so, and then recorded all the strains, because that's how we did all the calibration. So if you're going to do an SPMT move and give deflection limits, rest assured that they are going to calibrate for that. Okay, is it possible to get a link for the video we just saw? Absolutely. I'll have Raphael, I send the links to Raphael, and then he can distribute the links. Can you go to the next page? Is there any more questions, Raphael? Okay. What types of joints were used on the bridge? That I don't quite recall, because we were so immersed on the the whole design process. So the substructure design was not done by our office. That was done by our friends in Adelaide, Jacobs Adelaide, and they also designed the joints as well. So I'm gonna owe you that response. What is the reason to use shell element for the deck instead of solid element? For the type of analysis that we are doing, we felt that the shell element would have done its job appropriately, primarily because using the solid element, we probably would have to go. We are not really familiar with the solid, but looking back, maybe that's something we should have investigated. But I feel fairly comfortable that the shell element that is provided within the program can do its conclusion is that all the stresses that we got from the program, we transform into strains, and they were, and when they did the calibration, flexing the bridge, we were pretty close and within a reasonable range for the estimated strains that we came up with. What program do you use to create the animation of the move? That was done by the authority. That was not done by Jacobs. That was done by the South Darlington upgrade project. There is actually a website for the South Darlington project, and I'll send that link to Raphael as well. Did you consider pre-compressing the concrete deck by casting the girder high at the interior supports, having the deck in compression during the SPMT move? No, we didn't. We just primarily follow. You see, when it comes down to design builds, there's a lot of things that the designer wants as a wish list, and we had our wish list, but at the end of the day, the contractor is making the calls, and one of the things that we had on our wish list, we tried to push it very hard, was not to use a fairly thin web, and the contractor said no, I want you to use the 16 millimeters. So no, we didn't look at that pre-compression of the concrete. How are the dynamic impact effects, however small, during the move were considered in the SPMT analysis? Yes, we did consider that, even though it's unlikely. You might have situations where you have a SPMT wheel that is going to sink on the dirt, and which we actually had on the first bridge move, so they had to back it up and put steel plates so that it could go over. We did apply a impact factor of about 25% for the dynamic effects during the move.